core of a subject is sometimes most important considering the mathematical calculations. Well, topology has been a subject which has baffled a lot of young minds, those who are studying mathematics or embarking into their master's journey in physics or mathematics. The subject topology itself has created a kind of a confusion, not in terms of mathematical solutions or finding mathematical equations, but in terms of building up the concept. The more higher we grow up in terms of mathematical evolutions, you will see that things becomes too abstract. Things are not easy to visualize. Things are not easy to comprehend. And that is the core of getting the difficulties. Topology is a branch of mathematics which deals with a lot of problems in terms of viewing those abstract objects, their shapes, their behaviors, how they behave in terms of space, time, set theories, closed sets, and all those stuffs. So what I'm going to do in this video is that I will keep aside the mathematics of topology for a kind of a separate video, but I will try to give you more of a visual demonstration in making you understand the basic objective fundamental concepts of topology, how they are, so that when you do with the mathematics later and when you solve the equations, what becomes easy is that you already know and visualize in your mind how things are, how things behave, how they bend and they curve and they twist. So the basic objective of today's video in topology is to give you a visual demonstration, a kind of an intuitive approach in understanding the fundamental concepts of topology. My name is Shaunak. I teach in a college and I have been dealing with topology, and I welcome you to watch this video on my channel Physics for Students. A warm welcome. First of all, we need to understand the meaning and significance of the term topology. If you see here on your screen, I have given the original Greek form, and it says that it means topos, which means place and location, and topo and logy means subject. So that means it is a subject which deals with some place, local, locations, etc. Now, I would also like to keep a close watch on your screen, see what it means. Topology studies properties of spaces that doesn't change if they're distorted, wrapped, or twisted. This is the key. That means we are dealing with certain type of geometrical shapes which, if they are bent, turned, or distorted, some of the objects or the properties won't ever change. Why they won't change, that is a different issue. But what we need to understand now, that if things do not change, if they remain invariant, then for physicists or mathematicians, it becomes relatively easy to solve with shapes and sizes that remains same when they're distorted. That means we are into a branch of mathematics, or we are dealing with certain geometrical shapes, which if required, they will change, twist, anything, but some of the things will remain the same. Now, when we say that things will remain the same, that means we are dealing with a specific property. I remember that I made a long back a video in which I used a certain clay materials to really show you how the distortion happens. And if time provides, I would love to make another small video on that. So that means what you can understand, that the shape of a square or a square would be something which is similar to that of a circle. So if you see on the screen, you will see that I have shown that the square is similar to that of a circle, but that is not similar to a figure 8. I don't have those materials right at this moment, otherwise I would have shown you that all those things, if they are bent or twisted, that square can be made in a kind of a circle, the circle can be made back to some kind of a square. These things change. That means there is a distortion, there is a change in things which are taking place. One form changes to another, but not necessarily that form will again take the shape of another. It doesn't. So right on the screen, as you see, the famous example of homeomorphism, where the cup is turning to a donut and the donut is turning back into a cup. So that is why you will see that I have given arrows on both sides. Now the cup turning to a donut and the donut turning to a cup is a very typical and a classical example of topology. That means this particular shape of the cup, when it is turned into a donut and when it is going back, that means the function and its inverse function is also smooth and it is true. I mean to say, again, you will say that I'm using mathematical terms, but I'm using on a very easy manner. So till now, we have understood the definition of topology. We have seen that certain things changes, but certain properties will remain invariant. So a circle might be topologically similar or homeomorphic to that of a square, but certain shapes won't follow that rule. Okay, so now let us look into the screen. I have written that topology is the area of mathematics which describes the properties of objects that remain unchanged when you're allowed to bend. So you see, I have shown here the circle equals to a square, and that square is again equal to a rectangle. That means whatever the properties that lies within a circle will be that similar to a square, which will be similar to a rectangle. So the property of that object over here will be the similar over here, will be the similar over here. That means a circle is topologically equivalent to a square, which is equivalent to a rectangle. But remember, geometrically they are not the same, they are different. So now you get close to the difference between geometry and topology. So geometrically these shapes are different, but topologically they are the same. Now here comes the number one utility of learning topology. That means over abstraction and in the applied mathematics, when we deal with certain shapes and objects which are different, sometimes it becomes very difficult to distinguish between two objects, right? That means if we can formulate a set of rules for a circle or a shape similar to that of a circle, then if that shape deforms to another shape which is more or less homeomorphically or which more or less are similar, that means that whatever the properties that lies within that circle will be the same on the other object. So it becomes easier for geometers, mathematicians, physicists in order to study abrupt, abstract shapes and sizes, that if we can just get hold of the get hold of the property of one particular shape, and we can see that topologically they are the same, then all the properties in the other abstract shapes are equal. Don't you think that is really astounding? That's a great advantage for studying topology. Now, before we go ahead in this video, we understood what is a topology more or less. We have understood that it deals with shapes and sizes which are different, which changes, but certain objects doesn't change. But most important is that at all, why do we need topology? We are okay with geometry, we are okay with differential geometry, hyperbolic geometry. What is the need? That is coming up in the next part of our video. Okay, now you see, what I would like to tell you is that the need for the topology arises with the need of the changing human demand. So everything changed, the technology changed and everything changed. So the mathematical abstractions rules also changed. So right on your screen, you will see that a torus or a cup and a ball, these things, as we have seen, that they can be changed into any shape like circle, rectangle, square and anything. So a circle, as I told you, is topologically similar to that of a square, which is equivalent to that of a rectangle. Now here comes the question that why do we need topology? Now just try to imagine that in Euclidean space or in metric spaces, when we are dealing with distances between two objects and so on, what happens is that whenever there is a notion of a distance, so for example point A to point B, this point to this point, whenever there is a notion of a distance, we are getting bounded by a metric system. We are getting bounded by a metric system. Whatever the metric system will tell, we are going to follow with that metric, isn't it? So we are just like, if you have read or if you have seen the evolution of computer science, so from basic computing, then going to Visual Basic and C, C++, and then we moved into RDBMS, and then we go into a web-enabled system like Java and PHP, now that we have got Python for AI. So the system have moved along, the system has changed. Why? Because we always wanted to become platform free. So even in case of topology, same things follow, that mathematics wants to become now metric free, platform free. See on your screen, I have just shown you that if we take those shapes, deform, stretch and bend, we are trying to get a metric free, distance free system where the measurements will be invariant. And topology lets us talk about the notion of closeness, which in turn allows us to talk about things such as continuity, convergence, compactness and connectedness without the notion of distance. So topology actually generalizes fundamental concepts of analysis and calculus. So you see the basic core lies in getting platform free in order to get a metric system where we are not dependent on a specific metric. It is totally free. Now, as you see, when we talk of distance between 2 points, we talk about the triangles, angles, etc. Now we won't be talking about those things. We would be talking about the closeness between two people. Say, for example, one point and another point, how close they are. So closeness is something, a kind of a terminology in topology that we will use so that it shows the difference. You see this screen, you will understand things better. So the circle, cube, rectangle, square, triangle, all these are going from Euclidean, the notion, to non-Euclidean. So from specific shapes, we are going to irregular shapes. From Euclidean axioms, we are moving to topological axioms. And because from metric system, we are moving and throwing away that metric, we are finding a different kind of a space. And that space cannot be a Euclidean or a Cartesian space. No, it won't be possible because the notion of Euclidean and Cartesian space is being removed, and what we now need is what is called a topological space. So we have given away the notion of distance, we have given away the notion of metric, and now we are entering into a separate kind of a system which is metric free. We are entering into a separate kind of a space which is not the Cartesian or Euclidean space, it is a topological space. But before that, I would also like to demonstrate you quickly the need of a topology. I've just given a kind of a abrupt figure. See on your screen what I've tried to show you, that as we moved up the ladder, gadgets become smaller, it became all-purpose, tried to make things easy, tried to make things portable, easier to use, and it becomes user-friendly. So just what I was telling you, that if you see the evolution of computer technology, not only computer, as we move up the ladder, mobiles have become smaller, televisions have become smarter, people have become smarter than earlier, right? Why? Because we all want to make things much more portable, simple, easy to use, and all-purpose. So you see now a close significance between becoming metric free, distance free, and the same things happens with technology, that we are trying to make things which are totally platform free. So you see right on your screen, I have shown you that how the old computer is being replaced by a laptop, the mobiles have changed, the television have changed, and you see there are 3 points: generalized, smaller, and platform independent. These are the keys. That things become much more general, they become platform independent, and they become much smaller. So that is why you will see big equations once they are reduced to small equations. For example, calculus. We are not writing those big equations. Same happens with topology. Same happens with differential geometry. So what happens really is that in differential geometry, we use calculus in order to do calculations on a manifold, calculations on surface. Why do we need? Because again, we have generalized the Euclidean space to differential geometry, to a differential manifold. Same thing happens with topology, that we have generalized it. Now things will become much more compact, much more easier to handle. iPhones and Pro Max that are coming up. So just like IC designing and things have become a little bit more complicated because we want all those gadgets in one small specific space. That is why topology and the mathematics becomes a little bit difficult. Why? Because we have to solve a lot of things in a small space. So that is why the notion of set theory, etc. comes into play. So this is how the evolution of human technology has taken us forward, and topology is also not an exception. So now that we have understood the metric and we will go more into the metric in this part of the video. First, let us understand that what is the space that we are entering. That is, we are moving ahead from the usual Cartesian or Euclidean space and moving into what is called a topological space. So if you read any book of topology, don't worry, I will come up with a separate video on how to learn topology, what are the resources. But if you read any different a separate book on topology, you will see the topology that we know, that it deals with geometrical objects which are bent and then the invariance remains true. It is not like that. Topology also is a term which needs to be defined, and so is the topological space. So let us imagine that we have moved from Euclidean space now to a new space which is called a topological space, and this is what we need to know because we need to frame a new space. Have a close look on your screen. This is showing that Euclidean space is moved into topological space because it is a study concerned with geometrical shapes. So topological space is a generalization of Euclidean spaces in which the ideas of closeness or limits is described in terms of relationship between sets rather than in terms of distance. So the last line is very important. This is described in terms of relationship between sets rather than in terms of distance. So we now need sets. Now you might have a question right at this moment. Let me answer before that in case of differential geometry and topology, what is the difference? So differential geometry is something which relates to local manifolds. Topology deals with much more global scales. So because it is global, because it is big, so we need set theory, because sets are certain things which would sum up and then converge and then diverge and then make a union and intersection and all those things. So what we understand now is that topological space is a space which is generalized from Euclidean space, and it is now defining in terms of relationship between sets rather than in terms of distance. So the Euclidean space you can see on the screen is a space in which the axiom and postulates of Euclid's law are true. Metric space you see on the screen is a set together with a notion of distance called points. The distance is measured by a function called metric or distance, which is specifically d. Now, if you really want to go back and want to know more about the definition of metric space, how you can go to my video on topology, the last video which I made, the second last video, the fundamental concepts of topology. I have shown in details, but as I promised you that I won't be dealing with mathematics in this video, it's just a visual demonstration. So from Euclidean space, which deals with Euclidean postulates, we generalized into metric spaces. Metric spaces deals with functions, which makes even Euclidean space comes into a little bit smaller, which uses the function d. So, and further from metric space, we told that no, we need everything. We need a mobile, we need a camera, we need a WhatsApp, we need a television. Everything should be in my mobile. So the mathematicians told that we need everything to be platform independent, and we need something which is called a topology. Right on your screen you see Euclidean space generalized to metric space, which deals with the function d, and it is into topological spaces. So you see it generalizes Euclidean space. The concept of distance is replaced by closeness, a space whose elements are called points. This is important. So the points which were there, point 1, point 2, and we used to draw those lines, these are being replaced by the elements of a set. That means if there is a set A, for example, ABC or 1, 2, minus 4, that means these are points. What we understand is that it is just an evolution process. The mobile came through, the smartphones developed, the smart televisions developed, so is topology. So now we won't call those as points, rather we would call the elements of the set. Why we are calling them elements of a set? Simple, because we want to become free from metric, free from distance, free from any kind of a notion that we use. This is what is the need for a topological space, and this is how we move from Euclid to metric to topological space. However, there is something very interesting that we call what is the surface of a topology. That means what things really happen on topological space. It is not the same as Cartesian space that you will draw lines and things will evolve. I would like to show a very, very interesting topic on topology, which is called orientable and non-orientable surface, coming up next on this video. I would have shown you a kind of an animation, but somehow I cannot show you right here on this video. Orientable surface is something where you go around the surface, for example, an ant or an animal going around the surface, and when it comes out, it faces the same position. So I go around the surface like this, and when I come out, my head position or the distance is the same. Okay, first let us see what is an orientable surface. Here is a nice demonstration. Allows a consistent definition of clockwise and counterclockwise. See, on the torus, I have drawn the lines. It goes in this way, in this way. In case of a sphere, it is the same. So this is what is called an orientable surface. As you see on the right hand side, these orange people, when they're going around this torus, they're coming out in the same manner. So when you go around, you come back. That is called an orientable surface. Exactly opposite is what is called a non-orientable surface. Right on the screen you see a Mobius strip. Now this is a animation. Is a non-orientable surface. So when the crab is moving around, it has left and right flipped with every complete circulation. This would not happen if the crab would have been on the torus. That means when the crab moves through a non-orientable surface, and again when it comes down, the direction or the what we can say that the this is called the directrix. I'm so sorry. It is called the directrix. That is the direction. The directrix is being reversed. You see, Klein bottle and Mobius snail. These are examples of non-orientable surface. So here you see another illustration that this blue, this red, and this green. This shape, when it is moved continuously in a non-orientable surface, it has got a mirror shape. The shape is that of a mirror, right? That means it is reversed. The ant's head position is reversed. The shape is reversed. So when the directrix is reversed while going through that, that is called a non-orientable surface. It is extremely interesting for topology. So what we can summarize is this. An orientable surface is the one where if one moves along the oriented arrow, it is not reversed. Whereas a non-orientable surface is the one, if one moves in the oriented arrow, it is reversed. Arriving at the point where it is started, the directrix is reversed. This is something very typical to when we deal later with the surfaces of orientation and non-orientation. This is something which is important. So till now we have understood topology, definitions, how it evolved, topological space, all visuals, right? No mathematics right now. And we have also understood what is an orientable and non-orientable surface. We also need to know a little bit something which is called, because topology has got different branches, the tree branches out into different way. I would like to give you a very quick overview on what are the branches of topology coming up next in this video. Okay, so let us have a quick look on what are the branches or the different branches of topology. So we have got what is called general topology, algebraic topology, differential topology, and geometric topology, which is also called a low dimension topology, right? Okay, so quickly let us understand what is an algebraic topology. So algebraic topology, always we use the word algebra. That means it becomes, mathematics becomes easier. We assign values and we get the results most easily. So we replace the numbers with variables, that becomes easy to calculate. In general, that is what is algebra all about. Here also it goes with the same. So you see, I talked just a few minutes back that things becomes really difficult to distinguish between two shapes. So here also it happens the same. So have a quick look on your screen. It becomes difficult in topology to distinguish between things. Showing 3D space or not 4D spaces sometimes become difficult. So what we do is that we create algebraic objects or numbers. So you see, I have shown you that shape 1, if it is a shape, any kind of a shape, we are giving a number 2. And if that number yields to shape 2 and another shape 1, both of them yields the same number 2, then we call that these shapes would have the similar kind of a homeomorphism, or they will be something similar. The properties will be something similar. But you see again another shape 2, which gives a different kind of an integer, that is number 10. That means these shapes are classified into different groups on the shapes wholes and structures when we assign the numbers. Algebraic topology helps to classify different shapes, how a coffee cup is different from a baseball. So you understand that I have discussed in details, a little bit more details about algebraic topology in my other video. But here I just wanted to summarize that algebraic numbers or integers are assigned to that, then they're grouped. That is called homotopy and I'm not going into homotopy and other things. So they are grouped into a certain, so say for example, this is a group of, elephants. Okay, these elephants will have long, something which is similar. Maybe they will walk very fast and they will eat very fast, or they will have very long ears compared to that of normal animals. We give them, for example, elephant A group. Then we make it as elephant B group. So any number which is assigned to differential topology, quick look, let us look onto the screen. Differential topology deals with the topological properties and smooth properties of smooth manifolds. Differential topology may be defined as the study of those properties of differentiable manifolds which are invariant under diffeomorphism. Differential topology considers properties and structures that require only a smooth surface. It deals with properties of invariance and smooth manifolds. Now, there are certain technical mathematical things like diffeomorphism, etc. You can look into my video on differential geometry where I've dealt in details with what is a homeomorphism, what is a diffeomorphism. So in general, what I can say is that we take a shape and we differentiate that shape using differential topology. And if you find that the studies of the properties of the manifold, what is a geometric topology? Let us see. So geometric topology is the study of manifolds and maps between them, particularly embeddings for one manifold to another. So you see surgery, cobordism, algebraic invariance. These are fiber bundles. I don't want to get into these. These are mathematical terms which tells about geometric topology. So in geometric topology, we have two branches. One is the lower dimension, one is the high dimension. So lower dimension topology deals with 2, 3 or 4 dimensions. It has got knot surface, knot theory and braid surfaces. Geometry is the study of dimensions. So we divide it into lower dimension, these categories, and high dimension, these categories. Next, what is called a general topology. Right on your screen, you see that general topology is, earlier it is called point set topology. It is the basic study of topology, right? So general topology only we learn a little bit more because it is branches out to several other topologies. General topology normally considers local properties, etc. And it is the foundation of differential topology, geometric topology and algebraic topology. That means the branches that we are learning till now has got its root in the general topology. So you see that cover up the very quickly because there are many more branches. However, for this video, these are the branches of topology: algebraic, geometric and differential topology. We understood. However, we are now dealing with what is called a general topology because these would branch out to different other areas. Understood the different branches of topology. We have understood that we need a new space, that is a metric space. We need new things. The most important thing is that we started that video telling that topology deals with subjects which are related to geometric shapes and bending, but something will remain topologically invariant, which will help the geometers or the mathematicians to learn more. What is called a topological invariant visually, not mathematically? Let us find it out in the next part of our video. So in order to understand what is the topological invariant, I won't be talking about topology right now. I would go back to our good old college days when we are learning about vectors and what is called the basis of a vector. If you really understand during that time when we learnt about vectors and the concepts of basis of a vector, you might have noticed that when we do the base calculation for the basis of a vector, what happens is that the basis of a vector changes, however the main vector remains the same. So don't you think that that is also a property of invariance for a vector? That in order to move things from a flat surface to a curved surface, etc., the basis of the vectors changes, however the vector remains the same and it helps us to do the calculations. Quickly on your screen, what I would like to show you, you see this illustration. On the right hand side, we see the flat surface AX and AY, the two vectors. When they are moved into curved surface, the AX and the AY becomes bigger. However, the main vector A remains the same. So A is invariant. Now you see right on your screen, which is called a static frame of reference, and when it is rotated in a rotated frame of reference also, things become a little bit smaller and bigger. However, the vector remains the same. This is what is called the essence of the topological invariance, or anything which is invariant. So before we understand the topological invariance, I would also like to introduce a new concept which is called homeomorphism. We have seen that how the cup changes to a donut and donut changes to a cup. Broadly speaking, that is called homeomorphism. But mathematics has a kind of a strict definition. Right on the screen you can see homeomorphism is a correspondence between two figures defined by a one-to-one mapping, that is the function and the inverse are continuous. This is very important. The function as well as the inverse have to be continuous. That means a function f where x maps to y. That means 1, there should be a bijection. Number 2, f should be continuous. And third, the inverse should also be continuous. That means when the cup is turning to a donut, it is smooth, it is bijective, it is continuous. And when the donut is coming back to a cup, the inverse of the function is also continuous. So the function and its inverse are continuous. Okay, so let us see what is now why I am telling that topological invariant and homeomorphism are somehow related to each other. Here you see on the screen, homeomorphism is a continuous stretching and bending of the object into a new shape. A correspondence between two figures or surfaces or other geometrical objects defined by a one-to-one mapping that is continuous in both directions. So you see right on the screen the cup turning to a donut, the donut turning to a cup. The torus and the cup are homeomorphic to each other, and you can see this shape. This is a kind of a cube, but if I blow air into it, it suddenly inflates back to a kind of a sphere and or a ball, and that ball can again deflate back to what is called a square. We understood what is homeomorphism, but we are not clear about topological invariance. And there is a reason. I just used to use this term homeomorphism. Now let us come to what is a topological invariant. See on your screen, I have given it that a topology, in topology and related areas of mathematics, a topological property or a topological invariant is a property of topological space that is invariant under homeomorphism. That means it is a topological property, or a topological invariant is a kind of a property that is invariant under homeomorphism. Now, I hope that makes things clear, because until you understand that what is called homeomorphism, you won't understand what is a topological space. So that is why I first made you understand what is homeomorphism. So topological invariants are quantities with topological space that take on discrete values that do not change under continuous deformations of the shape. That do not change under continuous deformations of the shape. You see this demonstration. Space X has got a certain kind of a property under continuous deformation and change. It doesn't say change. That means this space A, when it evolves into certain other spaces, space A, space B, space C, space D, these are all homeomorphic to each other. So topological invariance is something that will not change under continuous deformations of the space, and where it is invariant. That means a space which is invariant under homeomorphism. That means we cannot do any kind of a stretching or bending in any shape, in any space. In any space. Obviously in Cartesian space we cannot do that. We cannot change a cup to a donut. It's typically in a kind of a Cartesian space. We can do that, but that won't be considered true because it doesn't follow the topological invariance. So topological invariance needs to go into a topological space, and topological space is a generalization of Euclidean space, and topological invariance is something which will remain unchanged under continuous deformation or under which is undergoing homeomorphism. Let's take another quick look. Here, as you see, I have shown that the cup and the donut is homeomorphic, a topologically invariant, and this inflates to a shape. So if a set X is equipped with some structure and makes X into a topological space, then by a topological invariance of the set X is understood a property, this topological space induced by the given structure of X. It seems a little bit confusing, but just to some clear example now using Cartesian coordinates so that things becomes easier. Have a look. These are called side, angle, and using the right hand side rule. They are congruent to each other. We remember those school days when we are given those theorems that find out whether these things are congruent to each other or not. So these are congruent to each other. Now, what is topological invariant? You see that angles are even congruent if they are flipped or rotated. So when they are rotated, they are still congruent. So can we devise a tool where we take all the polygons in the earth? We take all the polygons on the earth and we put it under something which is called a topological space. And let us try to find out a device, a rule where these polygons are invariant under any changes. I'm taking a hypothetical case. So I'm assuming that we take a kind of a rule where all the polygons present on this earth, the Euclidean polygons, and when they go, flip, turn, etc., that will be different. So now you see what I'm trying to do is that I'm using the polygons and group them into a form which is called topological objects. Right on the screen you see these polygons can take place into any shape. Congruency is replaced by topological invariant, and this is preserved under homeomorphism. So if we take all the polygons, then as we understood that with the evolution of scientific thoughts, these polygons are now can be bent, twisted, turned, anything. That means these polygons are no more the polygons. These polygons have been turned into any kind of a shape. And just as the congruency doesn't change when the angles are flipped or it has been rotated, in the similar way what we are going to do is that we are going to take the topological invariance as a kind of a congruency, but not the congruency. It is not called congruency. This is called topological invariance. That means just as congruency doesn't change when the Cartesian coordinates are flipped or rotated, topological invariance is also something which will not change when they would be turned, twisted or bent. So that is what is called invariance, and that invariance take place on topological space. Why do we need a topological space? Because these will not follow Euclidean axioms. So we create a space called a topological space. We replace those axioms with topological axioms like closeness, compactness, which we will learn, and these invariance property will help us to calculate further. So this illustration shows that these polygons, Klein bottle, torus, etc., these are topologically the same. So I hope that clears up a little bit of idea about how we move from the generalization of metric space to topological space and homeomorphism. Okay, so we come to the last part of the video. Now here I would like to show you a basic summary of what we have learned. So from Euclidean axioms, we are now moving into what is called a topological axioms. Now, I won't be dealing with topological axioms in this video because it is mathematical, and as I told you, the objective of this video is to give you a fairly intuitive and illustrative understanding of what is a topology. So here you see on the screen, Euclidean space got generalized into metric space. Metric space further got generalized into topological space. And these notions of closeness, distance, points, neighborhood, all these are notions which will help us to understand and make this system, I would say, metric free or distance free. These are dealt in the next part of the video. If you go to my other video, that is the beginner's guide to topology, I've already started slowly building up on the basics of topology. I would say what is closeness. I dealt a little bit with openset, but I'm going very slowly. The moment I jump into the mathematical abstractions, things will become complicated for you all. Sorry. So I really don't want to make things confused. I really want to make this video simple and illustrative. The reason being that, and as I told you, more than mathematics, what becomes equally important is that can you visualize, can you see, can you make a shape of all those frames in your mind? So that's it. I think that this video has given you a kind of a visual and intuitive understanding of the topology. So we will go into mathematics slowly next, step by step. And thank you for watching my video. Do subscribe to my channel, click on the bell icon and click on all to get all the notification from Physics for Students. This is Shaunak signing off and promising you to come back soon. But I'm very eager to know much more about how you're liking this series, what you want me to improve, what are the things you feel confused, and what are the areas that I can help you to improve more on the mathematical skills. Thank you very much for watching this video. Stay safe and happy, and best wishes for learning physics and mathematics. Bye.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.